Okay, hi everybody. Today we're going to talk about analog to digital conversion and some of the important considerations that we have to take into account when we do that process. So I want to start with an example here. Let's say that we wanted to measure this wind here, shown with these red arrows. We could use a cup and vane anemometer like this one, and the wind is going to come in, and these flat faces on the cups, or the convex faces on the cups, are going to catch the wind more than the concave faces and have a higher drag. And so that's going to cause these cups to rotate. And inside that cup and vane anemometer, we would have something that looks like this. This is a rotary shaft encoder. And a rotary shaft encoder will take that rotation in the sensor and turn it into an analog voltage. And so what that looks like in a block diagram is like this here. So we have our environmental variable. We're calling it U. That's the wind speed in meters per second. And that's interacting with our rotary encoder. And it's causing that rotary encoder to output an analog voltage. We're going to call that E, and it's measured in volts. And then something has to happen to that analog voltage so that we can turn it into a digital voltage that we can then record or make a decision off of in our system to have some kind of response. So what is this puffy cloud here? What is the thing that takes in the analog voltage and turns it into a digital voltage that then we can use to do whatever we want to do in our system? So we call this the analog to digital converter. So our analog to digital converter reads an analog value and converts it into a digital value at some frequency in time. Since these analog to digital converters are hardware, we can't make an analog to digital converter that can read a voltage from negative infinity to an infinite number of decimal places at an infinite frequency. So that causes us to have to make some design choices. And so related to those limitations, we have to have an idea of what voltages do we expect. And so what voltages would we want our analog to digital converter to be able to handle? So we call that voltage EFSR. And so that's the full scale range, FSR, of our analog to digital converter. Then we need to know how many bins will we use to discretize the signal. So this determines what precision we're going to get from our measurements. Remember, this analog voltage is coming in and it has an infinite number of decimal place values because it's analog. We need to decide how many of those decimal places, in effect, we want to keep in our signal. And then we also have to consider how often do we measure this signal and convert it. I should say and. Because we can't just sample at an infinitely small time. We have to make some decisions. So you remember from your temperature sensor, our EG207, that only sends a sample once every 10 seconds. So the built-in analog to digital converter inside that EG207 only samples once every second. And so just in general, so the number of bins that we'll use is a number that is binary. So typically we had a really simple example is that, we might have these transistors inside of our analog to digital converter, and some number of those transistors will be high, such that it will be on, and some number of those transistors will be low or off. And so the number of those transistors will determine how many actual values we can report, and we'll get into an example of this later. But we're going to use the value M to represent the number of bins into which we are discretizing our signal. And then the sampling frequency, so how often in time we're measuring our signal, we're going to call Fs. So what do these values mean in practice? Well, I might have an analog to digital converter with a full-scale voltage range of, say, 0 to 5 volts. And the converter might be, let's say, a 6-bit converter. So what that means is we're using 6 high and low values to create the number of bins that we would have between 0 and 5 volts. So what does that look like? Well, in order to get the number of bins that we actually would be counting, we'll call that N. This number of bins would be 2 to the M. So in this case, that would be 2 to the 6, which would be 2, 4, 8, 16, 32, 64. So we would have 64 total bins. So our analog to digital converter is going to take any input analog voltage from 0 to 5 volts and put it into one of, or in this case, the closest one of 64 values between 0 and 5. This would be 0, this would be 5. And so we have some voltage value come in. And it is, let's say, we can sort of zoom in here. This voltage value might come in. And once we've discretized that 0 to 5 volts into bins, we might have one bin value here, and one bin value here, and one bin value here, and those continue going up and down. And so let's say this comes in and it's 3.48613 dot 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 dot. These decimal places will go on forever. And here we might have some value that is 3.4 let's say I want to do this right, 8 6, and this is 3.487, and so you can see that this is 3.4861, so it's much closer to 3.486 than it is to 3.487. So this incoming analog voltage comes in, it hits our A to D converter. Our A to D converter decides what is the closest bin for that value, and then that digital voltage will get reported as 3.486. So if we were to plot say, a voltage versus time, and this is the actual voltage, the actual analog voltage, and we had, say, two different analog to digital converters, how might they look different when they actually discretize the signal? So first off, we can have two different full-scale ranges. So let's say our first converter has a full-scale range of 0 to 2 volts. And let's say it's, I don't know, 3 bits. So our first bit would cut it in half, and then our second bit would cut those in half, and then our third bit would cut those in half again. So you have a 3-bit converter, that's 2 to the 3 number of bins, so that's 2, 4, 8. So now we should have voltage levels at something like 0, 1, and 2, and then halfway in between 1 and 2 would be 1.5, halfway in between 1.5 and 2 would be 1.75, and so we'd have bin values at every quarter of a volt. And so our second might have a different full-scale range. Let's just say, for argument's sake, it goes from negative 0.5 volts to 2 volts. This wouldn't be typical of an A to D converter, but let's just say it did. And we can see that if we still had the 8 bins for a 3-bit converter, these bins would have to be much bigger, right? So it's important to recognize that our full-scale range and our number of bits work together to determine how much voltage there is, how much voltage difference there is between each bin. So let's say this one had an even smaller number of bins. This one's a 2-bit converter. In practice, we would typically see 8 or 12 or 14 bits typically. Sometimes as low as 6 bits, but we're just going much smaller than we would normally see so that the effect is much greater and easier to see. So this is a 2-bit converter. We're going to have 4 bins. And so we have one there, and I'm not going to calculate exactly what those values would be. I should say, yeah, perfect. So if we were to use these two different A to D converters to digitize this signal, what would it actually look like? Well, if we start here at something like 1.5, our A to D converter in the first case is going to have a bin value at 1.5 exactly. And so this would come out as 1.5. And remember, we have some sampling frequency in time. So let's say this one samples every 2.5 seconds. So we're sampling on these red lines. And so we would go up, and our next sample, we would get this. So something slightly less than 1.5, if it was the actual value. But remember, we can only measure values that are on bin locations, and so this comes out as exactly 1.5 again. And so remember, our next bin location is at 1.25.
which is kind of like this height along here. And so it's not until we get to a value that is closer to 1.25 than it is to 1.5 that we would do that the data would actually switch. So at 5 seconds, we go up, and we're much closer to 1.5 than we are to 1.25. And so that value would get binned as 1.5. And then at 7.5 seconds, or somewhere here, we're still closer probably to 1.5 than we are to 1.25 because we're right at like 1.4. So we would be rounding up. And then at our next value, we sort of get really close to 1.25 exactly, so that would be our 1.25. I guess I should have used another color that would contrast better with the magenta. But here, so we would see 1.5, 1.5, 1.5, 1.5, and then 1.25. And then somewhere out here, we might actually bin down to 1. And so at 12.5 seconds, we might bin at 1. And then at 15 seconds, we would round to 1 again. And then we would see, if this goes 30 seconds, 15 is the midpoint. And so we would kind of see that curve reflected since it's kind of symmetric. And so we'd get something like this. And so our discretized curve in the first case would look something like this, which is not a bad representation. We can still see that there's some locations where we have very obvious errors, but we kind of get the general gist. We can see ahead of time that our 2-bit converter is going to do a much worse job. I'm going to show this one in green. And so you'd see if we have a bin value here, even if we're sampling at the same time frequency, these ones would all be binned to that similar time level, that similar voltage value. But then we aren't going to switch to this lower bin until we're more than halfway between these two bin values, something like here. So then this next one, for the green, is also going to be in this high bin. And then this one, and this one are all going to be at that lower bin value. So if we go across, that's about here. So we get this, this, and this. And then our next bin value is way down here. And so it doesn't look like really any of those data points are closer to that than to up here, maybe the final one. So what we would get is this one, then probably this one, and then now maybe we are closer to this one here. So you can see the green curve would then end up looking like that. So much cruder, much more error between the actual magenta point and the green points. And so as I made the point that the full scale range and the number of bits interplay to sort of create that difference in voltages between the bins. We also have to consider, like I said, the sampling frequency. One idea here is that in the really high frequency case, if we only have a small number of bins, even if we sample at an incredibly high rate, we're still limited to those bins. And so we would just get a bunch more points that would make up our curve, but we'd still have this dramatic step here, and we still wouldn't get anything that looks like the magenta curve. Now, if we have a huge number of bins, but very small time sampling, that's not quite as bad, but we still can introduce some error that way. So let's take an extreme case. Let's say we were really good. We could get almost the exact value due in our discretization. I'll draw it in blue. But we're only sampling every 5 seconds. So we take one sample here at 0, and then we take another sample here at 15, and we're going to get exactly 1 volt. And then we're going to take another sample here at 30 seconds, and we're going to get 0.5 volts. So we're going 1.5, 1, and 0. What does that curve end up looking like? Let's see if I can draw it as a straight line. When we connect those points, we can see that the only curve you can assume through those 3 points is that straight line. And so if you were to try and interpolate what the actual voltage is at any time in between your sampling points, you'd be introducing this error that's not due to the size of your bins, but it's due to the fact that you're only sampling every 5 seconds. And so some final considerations regarding power consumption and cost. As our number of bits in our converter goes up, oops, we did M as the number of bits, I believe, right? Yeah. I guess we did M as the number of bins and N as the number of bits. So it looks like maybe we conflated these. Hopefully that relationship was clear, where the number of bins is 2 to the M times where M is the number of bits. So let's stick with M for now. I think I conflated them along the way. So as the number of bits goes up, our cost goes up. Similarly, as our sampling frequency goes up, our cost goes up. Because we need better and more precise circuitry in order to do both of these things. We need smaller transistors, and we need faster flipping of our circuits in order to get higher frequency. So that will go up with both of those. Now, with our sampling frequency, as that increases, our power consumption goes up. Because let's say, when we have a situation where we only have a limited amount of power, like when we're using a battery, every time we generate the signal to take that data, and every time we read it, and every time we convert it, all of that consumes power. And so if we're doing that 1,000 times a second, or 100,000 times a second, or 1,000,000 times a second, we're suddenly now utilizing that small amount of power it costs to take the measurement at an incredibly high rate. And so our total power consumption can go way up because of that.